So, good afternoon, everyone. I would like to welcome you all uh, for a technical event for this month. So, I'm very happy to welcome Dr. G.H. Thanki, who is a well-known person in the field of consultant for Corsair Consulting Private Limited. Today, he's here to talk on a very interesting topic, which is on beyond monitoring, leveraging AI and digital twins for predictive corrosion resilience. Let me just introduce Dr. Thanki. Dr. Thanki is a globally recognized corrosion management expert with over 45 years of experience in industry, research, and consultancy. He has advised organizations like World Bank, UNESCO, and leading firms in Europe. As a head of GSFC Research Center, he pioneered real-time corrosion monitoring and life cycle cost analysis. He has trained professionals across 80 plus companies. He has presented India in international arbitrations and received top honors, including the NACE Lifetime Achievement Award and the Indian Achievers Award from the Vice President of India. So we are highly obliged for you to accept our invitation, sir. And I would like to welcome you from the ICOT team. And I may request you to please start your presentation.
Thank you, sir. Thank you.
Yeah.
Is it my screen is visible to you people?
Not yet, sir.
Clear visibility?
No, it's not visible yet.
Oh, fine, fine. Good morning and good afternoon and good evening to
Sir,
all
we can't
to
see
our
your presentation.
beg your pardon?
We can't see your presentation yet.
You can't see.
So,
Is it okay?
no, no, it's not visible.
My first slide is seen by you, know?
No, no, it's not shared yet.
Oh, sorry, sorry. It's to be said. Mm, sharing button is not seen here.
It's a green color button at the bottom for share.
Huh?
It's a green color button at the bottom, share.
On the basket team, then it is another one. Explorer, share button. Mm, it's not visible on my screen, sir. Hello, Arpit. हाँ this share button I think हाँ शेयर बटन वो बार में दिखाई क्यों नहीं No, 1 minute. Let me try. Repeat. Wait a minute. Please hold it. आ गया है ना? ओके ओके, थैंक यू। हाँ जी, हाँ जी। ओके। नहीं, म्यूट नहीं है, ऑडियो पर लग दिया मैंने। एम आई ऑडिबल नाउ? हाँ। ओ, थैंक यू। तो मैं मेरा कैमरा बंद कर देता हूँ भैया। ओके। हाँ। Good morning, good afternoon, and good evening to our esteemed audience joining us once again from across the globe, from the Americas to Asia and Europe to Africa. It's an absolute honor to be invited back to this platform. The overwhelming response and a positive feedback from our previous session confirm that challenge of corrosion is not just a technical problem, it's a universal problem imperative. Just hold on. I will close it later. Where it has gone again. Ah, thank you to the organizers for this second opportunity to connect with such a dedicated multinational group of experts. Our last session, we set the stage for smart corrosion management, focusing on the foundational shift from manual inspection to connected digital monitoring. Today, we are not just monitoring, but how we can predict that we are seeing again. Again, thus, sir, I want to close it again. Thank you. The India AI Impact Summit is effectively a bridge. One will search how it has gone. Yeah. As the India, it's a good news just around the corner. As the India AI Impact Summit 2026 scheduled for February 16th to 28th, that means today 17th, in New Delhi unfolds at a pivotal moment for industrial science. We too convene on a virtual platform introducing our webinar on the strategic roadmap to predictive resilience. While AI for chatting or art dominates headlines, its application in material discovery and corrosion control represents a multi-billion dollar shift in our how we build and protect global infrastructure. Summit Science and Planet Chakras working group will like highlights we are moving from trial and error to predictive design. Hosting one minute sir is coming on the way. The AI Impact Summit 2026 at Bharat Mandap, New Delhi. So it's not a policy meet, it's a highly technical symposium where material science and industrial relations are front center. The digital twin visionary hook. It's
So you are muted, sir. You are on mute. Thank you, sir. You are on mute. Yes.
Let us look at how we are turning unforeseen failures into managed outcomes. Corrosion is silent, it's reckless. And traditionally, it's always been one step ahead for us. Until now, today we are shifting from a defensive posture to an offensive strategy. By leveraging AI and digital twins, we are finally moving beyond monitoring like this. I am thrilled to show you how we are building the roadmap to true predictive corrosion resilience. Let us go ahead. Now, the vision of predictive digital twin sounds like a magic, but it's actually built on a very specific, robust foundation. We can't predict the future if we don't understand the present. That brings us to our first critical pillar, the data acquisition and management layer, or what we call DAML. Think of DAML as the central nervous system of this entire corporation. If the sensors are the eyes and ears, DML is a bridge that carries signals into our virtual brain. Without a standardized, secure, and high quality data layer, and even the most advanced AI is essentially flying blind. Let us look at why this layer is the make or break stage for your corrosion strategy. The global industrial complex is currently undergoing a structural transformation in asset management, driven by the unsustainable economic and environmental cost of material degradation. Corrosion, often characterized as a silent destroyer of infrastructures, accounts for an estimated $2.5 trillion in annual economic losses and globally representing approximately 3.4% of the global gross domestic product. For the diverse audience of stakeholders, the challenge is not merely technical but existential, affecting sectors ranging from marine transport and oil and gas to renewable energy and civil infrastructure. Traditional corrosion monitoring, historically reactive, periodic, and labor incentive, is being replaced by a new paradigm, predictive corrosion resilience. This approach leverages the current convergence of high fidelity digital twins, that is DT, and artificial intelligence, that means AI, to synchronize the physical state of an asset with a virtual counterpart, enabling proactive intervention before catastrophic failures occurs. The global economic and environmental imperative. The financial burden of corrosion translates simple maintenance budgets impacting national security and global sustainability goals. Research conducted by the Association for Material Protection and Performance indicates that between 15 and 35% of corrosion cost, equating to as much as $875 billion annually, are preventable. The application of currently available and emerging corrosion control practices. High stakes environments such as the Gulf of Mexico, equipment failures due to corrosion represent an annual cost of approximately $2 billion. For water infrastructures in North America, corrosion contributes to over 260,000 pipe failures annually, adding $2.6 billion in repair costs to municipal budgets. Beyond the direct financial implications, the environmental cost is profound. Approximately 40% of global steel production is required simply to replace materials that have already corroded. A cycle of responsible for 3.2% of global CO2 emissions. For companies operating under increasingly stringent environment, social, and governance, that means ESG, quite popularly known as that frameworks, the shift toward predictive maintenance is a primary lever for decarbonization. Now I've tried to give you one tabulation on this global corrosion impact by sector and geography. We'll be making the table in sector, annual global cost, regional drivers, and critical failure modes. Say total global cost, 2.5 to 3 trillion dollar. Regional drivers are high salinity coastal regions, industrial hubs, and characteristic is pitting, structure thinning, and stress cracking. This is total global cost in which we are showing the critical failure modes. Oil and gas, 1.37 billion direct. Middle East, 32.5% market share, and Gulf of Mexico. Sweet, this is the failure mode. Sweet CO2, sour H2S, and microbial MIC. Infrastructure, 2.6 billion through water only. Regional drivers are USA, Europe, and India. Concrete rebar corrosion, bridge, beam decay. Defense, 20 billion US dollars by US DoD. Global naval and air fleets, critical failure boards with galvanic coupling, atmospheric salt spray, and environmental, 3.2% of global carbon dioxide, global steel replacement cycle, early coating failure, and leak-induced spills. Let us see the strategic roadmap to predict resilience, how it works. The transition from a no-twin state to a fully autonomous, self-healing infrastructure requires a structured progression through levels of technological and organizational maturity. Just a minute, sir. 1 minute. This roadmap provides a framework for organizations to evaluate their current standing and plan for a phased integration of AI and digital twin technologies. Like this is the way this roadmap I have tried to show you. Let us say phase one, how we start. This is the foundations and real-time connectivity. That is we label as the maturity level 0 to 1. The initial phase focuses on overcoming the limitations of status quo maintenance, which is typically characterized by disparate manual records and lack of real-time visibility into asset health. Let us start level 0, that is passive. Maintenance is purely reactive. Inspections occur based on fixed calendar dates or after a failure is detected. Data is often siloed in paper logs or isolated digital spreadsheets. Level 1 is startup. The organizations begin the twin transition by deploying Internet of Things sensors. This level focuses on real-time data capture and basic visualization. Operators gain a dashboard view of parameters like pressure, temperature, and current wall thickness, but analytics are limited to simple threshold alert. Phase 2, contextualization and prediction. That is what we call as a maturity level 2 and 3. In the second phase, the digital twin evolves from a simple monitoring tool into a sophisticated forecasting engine by integrating historical context and advanced physics-based models. Level 2 is progressive now. The twin incorporates historical inspection records and normative benchmarkings. By comparing current sensor data to years of maintenance history, the system can identify deviations from the normal degradation curves. Level 3. This is the threshold of predictive maintenance. The twin couples real-time data with machine learning and physical process-based models. It can now forecast the remaining useful life, RUL, of a component with high accuracy allowing teams to replace assets precisely before failure occurs. Phase 3, optimization and autonomy, maturity level 4 and 5. The final phase leverages the full power of AI, not only to predict the future, but also to optimize operations and maintenance strategies actively. And then comes level 4, optimization. The virtual twin allows for high fidelity what if scenario testing. Engineers can simulate the impact of changing of chemical emitters, adjusting flow rates, or applying a new coating type in a risk-free virtual environment. And level 4, we are reaching to autonomous. At the highest level of maturity of digital twin becomes a self-optimizing system. It reduces the optimal scenario for asset longevity and environment safety and can enact controls such as adjusting cathodic protection current autonomously. Let us have the easier twin. Now let us have the overview of all the system. VSC ML01, passive, manual inspection, siloed, historical only. It's a purely reactive one. Then we raise to number 1, the starter, real-time monitoring, IoT sensor streams, and descriptive and alert-based. The third, progressive, historical context. It has got historical context along with it. Then data integration comes with the IoT plus past maintenance logs, history. Then decision mechanism is diagnostic and trend analysis. Then comes to maturity level, predictive forecasting, multi-model data plus AI models, and prognostic and RUL calculation. Optimized scenario situation, virtual what ifs testing, and, prescriptive optimization. And then last comes master, autonomous action, closed loop self-correction, and AI-driven direct control. Building a predictive system requires a robust cyber-physical architecture that ensures bi-directional data flow and model accuracy. This architecture is typically divided into 4 primary layers, each fulfilling a critical role in the resilience ecosystem. The physical asset and sensor layer. The foundation is the physical infrastructure, whether it be a section of a subsea pipeline, a wind turbine tower, or a coastal bridge. This layer is embedded with diverse sensors that act as the eyes and ears of the system. Ultrasonic thickness sensor. This measures the wall thickness of metal pipes and tanks, providing high precision level of the material layers. And comes electrochemical sensors. These monitor the corrosion potential and current density of an asset, offering early detection of protective coating failure. And then comes the corrosion coupon, physical metal strips inserted into the environment that mimic the asset's material, providing ground truth calibration for the digital models. Environment sensors. These track ambient conditions such as humidity, temperature, pH, and the concentration of corrosive species like fluorides or hydrogen sulfide. Now let us come back again to DAML. The DAML acts as the bridge between the physical and virtual world. It handles the transmission, processing, and organization of vast amounts of data generated by the sensor layer. Key challenges in this layer include managing data quality, ensuring timely transmission over network infrastructure, and implementing security protocols to protect critical infrastructure data from cyber threats. Standardizing this layer using frameworks like ISO 23247 ensures that systems are interoperable and scalable across different assets and geographics. Here is a case which I try to get instead with the help of the AI, the data acquisition and management layer, DAML. It functions like this. the multimodal AI and simulation layer. This is the computational engine of the digital twin. It integrates ultra high fidelity simulation model with data driven AI algorithms to mirror the structural behavior of the asset. Physics based modeling. These models apply established principles of thermodynamics, electrochemistry, and fluid dynamics to simulate degradation processes. A fundamental mathematical representation of corrosion progression over time is the wall thickness degradation rate. For example, this is the way what we can consider. In this expression, dW by dt represents the rate of change of wall thickness, which is a function of corrosion rate constant K, depending on temperature, acidity, carbon dioxide concentration, velocity, etc., and the specific law regime within the system. Now, let us see the AI and machine learning modality, how it comes into. AI complements physics models by identifying non-linear patterns and anomalies in complex datasets that theoretical equations might fail to capture. Let us say the computer vision CV. Algorithms like YOLO, that means known as you only look once, or CNNs, that means convolutional neural networks, are used to analyze drone and robotic imagery for rust detection, fitting identification, and coating degradation, often achieving over 90% accuracy in defect localization. It's a wonderful thing. Time series forecasting. Recurrent neural networks, which is known as RNNs, and long short-term memory networks are employed to predict future corrosion rates based on historical environmental fluctuations. Let us break this down in everyday language. The problem, for example, is we want to predict how fast metal will corrode or rust in the future. Rusting depends on things like temperature, humidity, and pollution levels. When and change over and which change over time. The ideal is if we look at past environment data like yesterday's humidity, last week's temperature, last month's rainfall, we might spot patterns. And those patterns can help us guess what the corrosion rate will be tomorrow or next year. The tools, recurrent neural networks. Think of this like a memory friendly calculator. Unlike normal calculators that forget everything after each step, RNAs remember that happened before, what happened before. This makes them good at handling data that comes in sequence, like weather day by day. Long short-term memory networks. These are a special kind of RNA. Imagine RNAs as people with a short-term memory. They remember recent events, but forget older ones. LSTMs are like people who can keep both short-term and long-term memories. They are better at spotting long-lasting trends like how seasonal changes affect corrosion. In short, RNS and LSTMS are smart tools that study past weather patterns to predict how quickly metal will rust in the future. Virtual sensors. In areas where a physical sensor placement is impossible due to heat or accessibility, AI models can estimate corrosion risk by interpolating data from nearby sensors and environmental models. Let us say the feedback and control layer. The final layer ensures that the insights generated by the digital twin lead to tangible actions. This can involve triggering automated maintenance workflows, adjusting the injection rates of corrosion inhibitors, or issuing critical alert to human operators for immediate intervention. Let us put this in the everyday term, the feedback and control layer. Think of the digital twin, a virtual copy of a real machine or system is a smart advisor. It doesn't just study and predict. It also makes sure those predictions lead to real world action. Let us see the everyday analogy. Imagine a smart car how it functions. The sensors notice your tire pressure is dropping. The car system does not just show you a warning light. It can schedule a service appointment automatically, like automated maintenance flow, adjust how the car drives to reduce strain on the tires, like adjusting corrosion inhibitor injection rates. So this is the vehicle images. Send you a loud alert if the tire is dangerously slow, like issuing critical alerts to operators. Why it matters? Without this layer, the digital twin would just be a thinker that produces insights but never acts. With the feedback and control layer, it becomes a doer, turning knowledge into practical steps that protect equipment and keep people safe. In short, the feedback and control layer is the part of the system that makes sure predictions don't just sit in a report, they trigger real actions like repairs, adjustments, or errors. Now let us go with the regional challenges which I try to dig it out. The effectiveness of a predictive roadmap depends heavily on its ability to account for the unique environmental stressors present in the participating countries. Corrosion mechanisms are highly sensitive to local climate variables, which the digital twin must ingest as primary input parameters. I will take an example of marine and coastal environments. For nations with extensive coastlines or offshore assets, for example, USA, Norway, Brazil, Vietnam, Qatar, the marine environment is the most aggressive scenario. Splash and tidal zones, these areas suffer from accelerated wetting and drying cycles, maximizing oxygen and salt concentration. Digital twins in these regions must prioritize high frequency monitoring of salinity and chloride ion penetration. Another biofouling, the accumulation of marine organisms can create anaerobic microenvironments, favoring localized pitting and corrosion under deposits. AI models are particularly useful here for analyzing underwater visual data to detect early biofilm formation. Sargassum and hydrogen sulfide, recent seaweed decomposition events in the Caribbean and French West Indies have introduced H2S, hydrogen sulfide, into the atmosphere, creating highly corrosive environments for copper and zinc infrastructure that traditional model were not designed to handle. Arid and desert environments. In regions like the GCC countries like Saudi Arabia, UAE, Kuwait, corrosion management must contend with extreme thermal oscillations and sand abrasion. Thermal cycling, drastic day-night temperature changes can cause expansion and contraction in materials leading to microcracks in protective coatings that allow corrosive agents to penetrate. Night, Nighttime condensation. Despite low average humidity, nighttime cooling leads to condensation on surfaces. When combined with salt-laden sand particles, this creates hotspots for localized corrosion. Arctic and permafrost environment. Infrastructure in Siberia, that is Russia, northern Canada, and the Barents Sea like Norway faces the challenges of extreme cold and seasonal freeze-thaw cycles. Coating brittleness. Extremely low temperatures can make traditional protective coatings brittle and prone to cracking under mechanical stress. Permafrost stability. Ground level corrosion in buried pipelines is exacerbated by shifting permafrost, which can be placed unexpected mechanical loads on corroded sections of pipe. Let us see which is a table from the critical environment factors for predictive modeling. We'll consider the factor, we'll see the mechanisms of impact, high-risk geographics, and modeling requirement. Chloride, for example, destroys passive film, increases conductivity. It happens in Nigeria, Brazil, Vietnam, and coastal USA. And real-time salinity sensing plus electrochemical modeling are the requirement. Temperature accelerates electrochemical reactions kinetics. Saudi Arabia and UAE and India and Egypt are prone to this temperature variations. So Arrhenius based kinetics integration in digital twin. Then S2S CO2 causes sweet sour corrosion embrittlement. Iraq, Kuwait, Qatar, and Argentina are the high risk area in the world. Gas concentration monitoring plus metallurgical simulation is the model required in this particular section. Humidity, time of witness, provides the electrolyte for corrosion. Indonesia, Malaysia, Brazil, Central Africa are the high risk geographical zone, and time of wetness calculation from RH by the temperature data. And then comes the microbial MIC, biological byproduct induced acid attack, and various places like China, South Africa, Europe. Here the sensing with image analysis of surface deposits. Let us see economical as ROI. The adoption of AI and digital twin technologies is increasingly driven by a compelling business case with measurable improvements across financial and operational KPIs. For asset-intensive industries like energy and utilities, oil and gas, mining and metals, telecommunications, transportation and aviation, manufacturing, the transformation of maintenance from coastal center to driver of resilience is quantifiable. In short, maintenance is no longer just about fixing things. It is about measurable resilience, means proving with data that your maintenance strategy strengthens the organization's ability to endure, adapt, and thrive under stress. It's about turning resilience into a performance indicator, not just a vague aspiration. So it is really mind-boggling what we are experiencing. Financial performance indicators. Average ROI, let us see. Clients implementing digital twins for gas distribution networks report on average ROI of 250% within the first year. Here is how those impressive ROI and cost reduction results happen when gas distribution networks adopt digital twin technology. How digital twin drives ROI? Here is like this. Digital twin goes into the computer screen and collect all the data connected. So it is a sketch tight illustration of a uh, uh, digital twin showing how a physical industrial system is mirrored by its virtual counterpart with data streams connecting the two. The drawing captures a physical factory on one side, a digital replica displayed on a laptop screen, a third is data arrows, and a cloud symbolizing real-time connectivity. This visual emphasizes the essence of digital twins, a continuous loop of monitoring, simulation, and optimization between the real and virtual world. So, digital twins create a virtual replica of the gas distribution network, allowing operators to simulate scenarios, predict failures, and optimize asset performance without disrupting operations. So, data-driven decision making becomes very easy. by integrating IoT sensors, SCADA system, and AI analytics. Companies gain actionable insights in the system and improve the efficiency. Maintenance cost reduction. Predictive strategies typically deliver a 30 to 40% reduction in our maintenance cost by eliminating unnecessary inspections and prioritizing high-risk assets. Now, with the cost reduction, how? Predictive maintenance strategies. Instead of fixed schedules, maintenance is triggered by actual asset condition data, and this eliminates unnecessary inspections and focuses resources on high-risk assets. Early detection of anomalies reduces catastrophic failure, which are far more expensive to fix than preventive intervention. So cost savings is rapidly high. Studies show predictive strategy typically deliver 30 to 40% reduction in overall maintenance cost, aligning with industry dilemmas. Emergency repair avoidance. AI-powered failure prevention with up to 95% accuracy and can reduce emergency repair expenses up to 70%. That's a powerful statement. It highlights how predictive AI can transform maintenance strategy. So let us break it down. Key points. Emergency repair avoidance. AI system can monitor equipment, detect anomalies, and predict failures before they occur. Accuracy up to 95%. This suggests the AI can correctly identify potential failures in most cases, minimizing false alarms. Cost reduction up to 70%. By preventing breakdowns, organizations avoid expensive emergency repairs, downtime, and damage. Yeah, downtime and secondary damage. Asset life extension. Data-driven replacement planning and optimal intervention timing can extend the useful life of critical infrastructure by 25%. Here is how that concept plays out. Let us see. Key points. Asset lifecycle extension. Using data analytics, organizations can plan replacements and interventions more intelligently. Instead of replacing too early, that means wasting useful life, or too late, risking failure, AI pinpoints the best moment for action. It is 25% longer use, extending the lifespan of critical infrastructure, reduces capital expenditure, and delays costly replacements. Now let us see the OEM, that means operational efficiency metrics. Transitioning from manual to digital twin supported inspections can increase the speed of maintenance campaigns by up to 75%. Defect detection accuracy. The integration of AI and 3D scanning provides a 30% improvement in the detection of surface defects compared to human only visual inspections. Downtime reduction, real-time visibility, and scenario modeling minimize unscheduled outrage, which for an oil platform can represent millions of dollars in lost production per day. So now let us see the ROI and efficiency gains from digital transformation. Let us see the table. Maintenance cost metric. So he is performing that delta is a 30 to 40% reduction. Asset lifespan, premature development, extended life, 25% increase. Incident rate, high risk of failure, 95% failure prediction. You have the performance of the 60%. Inspection time, you take weeks and months manually. Digital twin, automated and robotic, 75% faster. Energy use inefficient due to degradation, optimized via health monitoring, and performance data says the 10 to 20% savings in energy. It's a big figure. Let us talk about ESG impact and corporate sustainability. In the modern industrial environment, sustainability means not wasting resources and keeping the planet healthy is no longer merely a reporting function. It has become a fundamental data and AI challenge. Predictive corrosion management is a primary contributor to corporate decarbonization and environmental stewardship goals. In today's factories and plants, being green is not just about filing cut the paperwork or checking boxes anymore. It has become a high-tech job that requires using computers and smart tech to solve big problems. One of the best ways a company can protect the planet is by predicting when pipes and machines will rust before it actually happens. By fixing things early, companies stop leaks, save energy, and prevent big accidents that hurt the environment. The connection between corrosion and CO2 emission is twofold. First, the energy intensive production of replacement steel accounts for a significant portion of global industrial emissions. And second, equipment operating at degraded efficiency due to internal corrosion consumes more energy. AI-enabled energy monitoring can detect this efficiency drops early, preventing 40 to 60% of maintenance-related carbon output. Studies have shown that organizations implementing predictive maintenance achieve annual avoided emissions between 500 to 1500 ton carbon dioxide. It also helps the waste minimization and resource efficiency. Predictive analytics extends the functional life of components, eliminating the need for premature replacement and reducing the volume of maintenance-related waste by 50 to 70%. Furthermore, by preventing leaks and rupture, these systems the risk of catastrophic environments, accidents such as oil spills or chemical leaks, which incur massive remediation costs and ecological damage. Let us say the automated ESG compliance. How? Digital twins provide a transparent, auditable trail of an asset's health and environmental performance. Like this, organizations can leverage autonomous data pipelines to automate ESG reporting, improving reporting accuracy by 95 to 99% while significantly reducing the manual workload for compliance teams. This is a very important criteria which are touching up standards, governance, and interoperability. For a global audience like us, the successful implementation of predictive resilience relies on a unified framework for data exchange and system interoperability. The absence of standardization has historically led to confusion and hindered widespread adoption. Digital twin, a global industrial mirror. I will show you how is it. Physical asset, real world machine, plant or infrastructure. For example, pump, turbine, pipeline, or entire facility. Sensor data, IoT sensors collect real-time data, temperature, vibration, flow, corrosion rate. Data flows securely to the cloud, so it remains untouchable afterwards. Digital replica, a virtual model that mirrors the physical asset, includes geometry, behavior, and operational history. Fourth comes analytics and simulation, predictive maintenance, stress testing, life cycle forecasting. AI and machine learning enhance decision making. Actionable insights, a very important criteria. Alerts, optimization, strategies, and performance dashboards enables remote monitoring and faster intervention, and continuously real-time updates between physical and digital. So this has resilience, efficiency, and sustainability. So digital twin mirror the metal and master the future. Here is the digital twin with all the 6 steps. You know now what we discussed just now. It is just I have told you the visual only. The ISO 23247 framework. It provides a standardized approach for the creation and management of digital twins in manufacturing. Its architecture is divided into the physical layer, the digital layer, and the integration layer. That means secure bidirectional connectivity. Adopting ISO 23247, compliant systems ensure that an organization can integrate diverse sensor technologies and AI performs without being locked into a single vendor's ecosystem. I'm just trying to give you by this vision. First, physical layer, down below, physical layer. The real world manufacturing environment, it includes machines, sensors, operators, and production lines. And this is where data originates from vibration sensors, temperature gauges, corrosion monitors, etc. Next comes the digital layer, that will be analytics and simulation, the brain of the digital twin. This is the brain. Processes incoming data using AI, simulation models, and predictive analytics, and then enables forecasting, anomaly detection, and virtual testing before real-world actions. And third comes integration layer, the bridge. The bridge. It ensures secure biodirectional data from using standardized protocols, allows interoperability across platforms, avoiding vendor lock-in. This layered structure empowers organizations to build scalable, vendor-neutral digital twin ecosystem. This is a very good thing to be practiced. If anybody is interested, they can definitely approach us. Industry-specific corrosion standards. Predictive models must also align with the technical standards from the Association for Materials Protection and Performance, previously known as NES, and the American Society for Testing and Materials. NES ASTM G193, it is standard terminology and acronyms relating to corrosion. NES TM0169 to ASTM G31, standard guide for laboratory immersion testing, crucial for calibrating digital twin models. And NES 3T199, techniques for monitoring corrosion and related parameters in field application. And ISO 19650, it guarantees cross-phase information, consistency, and data governance throughout the asset lifecycle. Let us see the futures. There are few slides now to go ahead. Future frontiers, agentic AI, and quantum simulation. The technological landscape for corrosion resilience is rapidly evolving beyond traditional machine learning. Emerging frontiers promote even greater level of autonomy and precision. It's exhibiting autonomous, goal-directed behavior and decision-making capability. Next generation frameworks are integrating agentic AI, agentic AI agents capable of autonomous decision-making and negotiation. In the context of corrosion management, these agents can negotiate contracts for anti-corrosive materials, optimize sourcing cycles, and adapt procurement strategies in real life time based on the predicted risk identified by the digital twin. Is it wonderful? It is really wonderful thing where we will be a lot of supported by such system. Really, we get lost in such type of negotiation area. Multi-model AI and self-healing systems. The international integration of multi-model AI allows system to simultaneously process sensor streams, visual inspection data, and textual supply documents. This provides a holistic insight into material performance that was previously impossible. Furthermore, research into intelligent paints and coatings with embedded corrosion inhibitors that are released automatically in the presence of moisture or mechanical damage points toward a future of self-healing infrastructure. Quantum AI simulations hold the potential to model the molecular resistance of emerging alloys and coatings under refinery-specific conditions with unprecedented accuracy. This will enable the design of materials that are tailored to the specific environmental stresses of each geography, be it in the hypersaline Persian Gulf or the acidic shale gas reservoir of Argentina. For the global community of engineers, managers, and policymakers gathered for this webinar, the transition to predictive corrosion resilience is both an opportunity and a necessity. I am addressing to you, sir, all my international community at the moment. The evidence demonstrate that leveraging AI and digital twins can reduce operational cost by 30%, extend asset life by 25%, and significantly contribute to global decarbonization efforts. To realize these benefits, organizations must prioritize the following strategic actions. This is only 2 slides now to go. First is assess maturity. Use the digital twin maturity model to identify current gaps in data acquisition and modeling capabilities. Second, standardize data. Adopt ISO 23247 and ISO 19650 frameworks to ensure scalability and interoperability across global portfolios. And third, integrate physics and AI. Move beyond simple black box AI model by integrating established corrosion kinetics and physics-based simulations into the digital twin. So tailor to the environment. Incorporate local climatic modulators such as time of wetness, salinity, and gas concentration as core input parameters for predictive models. Focus on wind. Align predictive maintenance deployment with high impact assets and critical ESG target to ensure rapid ROI and stakeholder buy-in. By moving beyond simple monitoring and embracing the transformative potential of AI and digital twins, the global industrial community can build a more resilient, sustainable, and economically viable future. So, we have spent decades being one step behind Rust and VR, but today the game changes. With AI, we finally have the crystal ball for asset health. Like this, it's time to trade manual guesswork for digital certainty. Thank you for joining us on this journey to predictive resilience, where we keep our plants running, our people safe, and our planet proactive. So, in the race against the time and corrosion, monitoring tells us where you have been predictive. AI shows you where you are going. Choose it to see at the moment. Thank you, gentlemen, for patient listening me. If anything is there, please reach to me afterwards whenever you wish so. I will try to address any confusion or any further link if you wish so. Thank you. Thank you a lot. Dr. Thanki takes the lead from you. Thank you.
Thank you, sir, for this excellent, insightful presentation. I think from moving traditional monitoring to AI-driven predictive corrosion resilience digital was extremely valuable. I hope that the audience has gained a lot of practical insight on how digital technologies can transform corrosion management and asset integrity. So once again, I would like to sincerely thank you for your time and the expertise. Thank you for all the participants also who have joined us today. Before we conclude, If you have any questions, you can please post them into QAM below, and we will try to take few of them today. The rest can be emailed it to me, and I will forward it to Dr. Thanki for answering, and we'll reply back to you. If you want to become member of ICOR, we have certain grades of membership, starting from student membership, which is free. We have affiliate and professional and fellow membership also. All these details can be found on their website, icor.org. And if you have any queries, you can please contact me to india@icor.org. So any questions further, you know, please post up and I'll try to take on that one. Gandhi sir, we have one question. What type of AI
Mhm.
model is required for prediction of pitting corrosion on shrimp anchor chains?
Mhm.
What type of AI models is required for prediction of pitting corrosion on ship anchor chains?
Naturally, it has to be very focused one. Otherwise, pitting corrosion will be not focused, understood. Otherwise, crevice corrosion will be mixed in that case. So you have to give the total detail of what type of pits you want to study for, whether it is for the active passive metal or with the carbon steel. If that data are generated, naturally we can develop that model in that case, sir.
Any more questions, please? What are the data required for making the corrosion prediction model for ship anchor chain links? What all data we need to be required for corrosion prediction model for ship anchor chain links?
More the data, we are more reliable.
What kind of a data we require?
That in that one, you have to be with a corrosion specialist to know the characteristic of the pits, for example. Right, sir? And with pit will develop with the very low pH when it goes down below in the pit bottom, corrosivity very high. So you have to collect more data. If any specific case is that, please come to me with specific area. I will be able to tell you what data are required to develop a model to finalize whether it is pits or crevice corrosion or general corrosion.
Is there any specific standard used for marine corrosion?
Yeah, standards are there in the ASTM standards will be given. I can definitely find it out and can give it to you, sir. Hmm?
That's all. Thank you so much, sir, for again joining us today and sharing your expertise with us. Thank you, sir.
Thank you, Professor. Thank you for
Thank you.
giving me the opportunity. Thank you.
Thank you.